Hello, I'm Nicholas Jenkins, an undergraduate honors student here at Georgia Southern University, and today I'd like to show you a little bit about my research on drill control surfaces, a piezoelectric approach, under the mentorship of Dr. Illy with the Department of Mechanical Engineering. To begin, I'd like to give a big thank you to Dr. Illy for his undying patience and enthusiastic support, always nudging me in the right direction with this research. I would also like to acknowledge the honors program for not only providing me a challenge, but giving me a unique experience throughout my college career. And finally, my family, for always supporting me every step of the way. I wouldn't have made it this far without them. Here, you can observe an overarching layout of what I will be covering in this presentation, starting with background briefing. We will go over piezoelectric technology so that you can become more familiar with it, as well as the control surfaces on aircraft, finally rounding out to why we are combining these two things to be used on drones. Next is methodology, where I will explain how I generated the model and obtained the results from the simulations using these models. We will then go over the data drawn from these simulations, namely pressure, lift, and drag, and then use those data to cover results in conclusion. Piezoelectric materials are piezoceramics that expand and contract when voltages are applied. Now, for those of you who are already familiar with piezoelectric piezoceramic materials know that it's typically used the other way around, where vibrations or other movements will cause the piezoelectric to generate electricity as a signal or power generation. For my purposes, I am attaching it to a sheet that is comparatively more rigid than the piezoceramic so that it can perform as an actuator and bend as seen in this figure here. Here are some traditional control surfaces for an aircraft. Starting with the wing section, we have ailerons. Ailerons help to roll the aircraft for banking in flight. Next, we have flaps. Flaps increase drag and increase lift, which is great for landings when you want a slow and steady descent. On your empennage section, you have elevators. Elevators help to change the pitch of the aircraft for changes in altitude, while the rudders help to yaw the aircraft and control banking in flight. Here, I want to focus on ailerons for my piezoelectric research because not only is the control surface one of the most important out of all of them, but it is also easily controllable by batteries, which drones already sufficiently provide. So to start my testing, I chose 4 airfoils from a bank of NACA airfoils, or National Advisory Committee for Aeronautics. Starting with the first airfoil, I could tell that it was a symmetric airfoil based on its symmetric shape and how it mirrors across the chord line here, which is from the leading edge to the trailing edge. Flying this horizontally in a wind tunnel would produce 0 lift, which made it a good control for my testing. Next, we have NACA 64208, which, as you can see here, the chord line slightly crosses the trailing edge, and this trend continues throughout. It's harder to see on 65210, but very easy to see on 65410. And this will produce more lift as air goes underneath the wing and builds up pressure at the trailing edge and goes off of the trailing edge. These last 3 wing designs also complement piezoelectric materials because they'll be easier to bend when the piezoelectric is powered. Pictured on the right is a final product of what you could expect to see in an ANSYS model after it's been meshed. To get to this point, I actually took the airfoils from the last slide and converted them to sketches in SolidWorks. When I did that, instead of modeling them as wings, as a body, I actually took the negative. As you can see here, there is a cavity where the wing should be. And by extruding a box around it, I was able to effectively test these in ANSYS by using these meshed portions here throughout the body as the effective wind tunnel. So when it made it to ANSYS, I actually did linear meshing on all of the models to make sure that everything had a uniform meshing and to make sure that the contour plots that I got from the testing were smooth and accurate. Proceeding with the same model that was just displayed in the last slide, I applied boundary conditions to this model. As you can see on the far left in this figure, there are many arrows around it. Going in at the far left, we have our inlet, which was set at 10 and 30 meters per second for each airfoil design. And the outlet was 0 pascals to represent no pressures at the outlet to allow the wind to go through with no resistance. On the middle, you can see a line that was drawn around the airfoil to represent the surface so we could get lift and drag along the surface. Lastly, you can see a plane inserted through the center of this model, which served as a location point for me to draw contour plots for pressures and velocities. With all of the original airfoils simulated, I proceeded to remodel them to have the piezoelectric actuator applied at the trailing edge. And you can see a little bit of this for airfoil 000834 on the left here, where this portion right here was the original airfoil as it proceeded at the trailing edge. And down here you can see a dome applied. This line right here represents the piezoelectric actuator at its deformation stage. This displacement you can see right here, 0.01, is in meters, and it actually represents the doming of this piezoelectric material, which you can see some of the properties on the right in these tables. The length of this arc was determined from the actual length of the actuator up here, 2.5 inches. And so by doing that, I was able to fully design a trailing edge for this wing. These are the three outcomes for NACA 65-410 airfoil, which all occurred at 30 meters per second alone. On the far left, you can see the original airfoil design subjected to the simulation. In the middle, it occurs at 30 meters per second at 0 volts, so this is with the piezoelectric actuator attached. And the far right is also with the piezoelectric actuator attached at 500 volts. If you notice in the middle, there is a large occurrence happening here with pressures all around, and it's even higher at this trailing edge right here because the flow is building up before it can actually flow off of the end of the wing. Over here it's slightly smaller, and that is because rather than the actuator curling more when it's powered, it actually releases the curvature a little bit. So it produces less lift when it is powered. So kind of counterintuitive to how ailerons usually work. When they're powered, they produce more lift. In this case, it's reversed. And that also helps with any sort of emergency situations where if it were to lose power, it automatically produces a lot of lift and a lot of drag to allow the aircraft to safely make it back to the ground. Tabled here are lift and drag components for all airfoil designs. If you look at lift and drag for both 10 meters per second and 30 meters per second, you'll notice that the drag is sufficiently less than lift, which is highly desirable. Highlighted on the right, this 19.74 newtons of force is the force produced between powered and unpowered states of a piezoelectric on the trailing edge of NACA 65-210, which is sufficient enough to roll a drone. Here's a visualization of the data you just saw in the last slide, and again NACA 65-210 comes out at the top with the most lift provided for both 10 meters per second and 30 meters per second, in addition to the difference we just observed in those tables, with the highest being 19.74. With that lift also comes drag though, where 65-210 again came out at the top. However, these drag components are way less when you compare their ratios to the lift that is also produced. Overall, piezoelectric actuators are a viable method for flight control surfaces. Lift was improved in the airfoils when they were applied, as you could see in the data table, and little to no drag was present. These differences in lift were observed when the actuators were powered between 0 volts and 500, and you could see that with NACA 65-210 where there was a difference in 20 newtons. Thank you for taking the time to listen to my presentation on piezoelectric actuators and how they can be used for controllable surfaces on aircraft.